Hi, everybody. Yes, I'm Cora Wheeler. I'm a graduate student at UC Irvine, and I'm going to be talking about star formation in satellite galaxies and what it takes to shut that down. I'd like to quickly thank my collaborators, John, Mike, James, and Eric. So there's this idea that falling into the virial radius of a larger host halo quenches the star formation in a satellite galaxy. But how efficient is the quenching? How fast does it act? And under what circumstances might it occur? My goal, or our goal with this project, was to investigate simple one-parameter models for quenching and compare it to observations from Sloan to get a handle on what's the best characteristics of a host-satellite pair that would correlate best with the quenching of a satellite galaxy. So our observational sample is a really nice sample coming from G et al. 2012. It consists of dwarf galaxies in the stellar mass range of about 10 to the 8 to 10 to the 10 solar masses. Luminous neighbors, which are just galaxies with stellar masses greater than about 2.5 times 10 to the 10 solar masses. And then in particular with the dwarfs, we're going to be looking at just 2 stellar mass bins that kind of span our sample. So here's a plot from that, using that data. It is the fraction of the dwarf galaxies that are quenched as a function of this projected distance to a more luminous neighbor. So basically you just find a dwarf, go out and project a distance, find the closest luminous neighbor that has a velocity offset of 1,000 kilometers per second or less, and then plot the quenched fractions. So there are a couple interesting things to notice initially just about this plot. One, beyond about 1 to 1.5 megaparsecs, the quenching fraction drops to 0. And this is the main result from Marla's work, is that once you get below a certain stellar mass, about 10 to the 9 solar masses, so, these galaxies don't quench themselves. There's no quenching in the field. Another interesting feature of this plot is the point at which the quenched fraction hits 0. It's about a megaparsec, which is several times larger than the virial radius of the luminous neighbors. So you might ask, what's going on here? Are these things being quenched out 2, 4, even more virial radii outside of their host halo? And I'll return to that question in a second. And then finally, I'd just like you to notice that even in the innermost bin, even within about 250 kiloparsecs from a luminous neighbor, the quenched fraction is low, only about 25 to 30%. And what this means is that quenching is inefficient, very, very inefficient. Okay. And then when considering this plot, and pretty much every plot in my talk, an important caveat. The distance to the luminous neighbor is not necessarily the distance to the actual host of the dwarf. If any of you remember my talk from last year, I'm sure all of you do, actually correctly figuring out which host and which satellite belong to each other is really challenging. And in particular, dwarfs out here, but beyond a megaparsec, probably don't have a host in the first place. This is just, this suffers from projection effects. But so just keep that in mind. Oh yeah, so if we really want to know what's going on physically, we need the full 3D information provided in a simulation. So to that end, we mock observed the Millennium 2 simulation, basically in exactly the same way Marla observed Sloan. We found dwarfs, which for our purposes are in the Vmax range 80 to 110 kilometers per second, and found the closest luminous neighbor in projected distance. Luminous neighbors in the case of the simulation have Vmax greater than 150 kilometers per second. Now, we didn't have to do this. We know what the hosts are. We know the 3D distance. We know all that in the simulation. But it's really important in order to be able to compare the two that we did exactly what was done in the observation. So we also wanted to make sure that our pairs had a velocity offset of less than 1,000 kilometers per second. Okay. Okay, so here, here's that same plot. And before I go on and show the simulated data, I just wanted to point out one interesting thing about this sample is because, as Marla showed, these things are not quenched in the field, which means that the actual quenched fraction that we're plotting here is the environmentally quenched fraction. These things don't quench themselves. So this provides us a unique opportunity to come up with these very simple one-parameter models with properties of the host satellite pair and compare them without the need to factor in the self-quenching of the galaxies. Okay, so let's just start with the simplest thing we could do, the model I kind of hinted at before. Something becomes quenched as soon as it becomes a subhalo, falls into the virial radius of a larger host. This is simulation data here. This is the fraction of things that are subhalos, the fraction of our dwarfs that are subhalos of anything. Once again, as a function of the projected distance to the luminous neighbor. Right away we can see that satellite quenching is far too inefficient to be caused simply by falling into the virial radius of a host halo. We're over-predicting the quenched fraction at all distances. But in particular, just for a second, let me draw your attention to the fact that we're not even reproducing the zero quenched fraction outside of a megaparsec. So even while we thought that all of these things out here were in the field, it turns out that between 3 to 10% of these things are subhalos of something. And that goes actually all the way out to 4 megaparsecs. So they can't possibly be subhalos of their luminous neighbors. They're way too far away. So they actually have to be subhalos of something much smaller. And we can see this if we plot now the fraction of our dwarfs that are subhalos of things that would fall in that luminous neighbor category, right? It doesn't really change much in here, but as we would expect, we actually now can reproduce the zero fraction at large distances. Another way to look at this is if we actually now, with the same x-axis, plot the virial mass of the actual hosts of these dwarfs. So just to be clear, we're still using the projected distance to the nearest luminous neighbor, but the y-axis here is the virial mass, not of the luminous neighbor, but the actual host of the dwarf. So we can get a sense of what type of halo these things are living in. And make comparisons between these two plots. So this is the median and the cyan, the green and cyan bands are the 68 and 95% confidence intervals respectively. So just as we discovered before, out here things have a very low mass, just as we predicted. But the other point I want to take away from this plot is that this drop off here is happening in exactly the same spot as the drop off in quenched fraction. So it means that this drop-off in quenched fraction is being set by the virial radius of the clusters, primarily, which is about a megaparsec. So it's not the case, thank you, it's not the case that these things are being quenched at even like 5 or 4 or 2 times the virial radii of their host. In fact, they're not even being quenched at 1 virial radii of their host, because quenching it's too inefficient. If that were the case, we would expect a 90% quenched fraction in the innermost bin, when instead we're only getting 35%. Or sorry, 25 to 30%. Okay, so I think we can safely say that this model, where something becomes quenched just because it's a subhalo, doesn't work. But what properties of the host-satellite pair could potentially be better predictors? Maybe the host needs to be bigger. Maybe the satellite has to have been orbiting for a certain minimum amount of time, or maybe the satellite has to have lost a certain fraction of its mass. And we're going to quickly look at those 3 models. Okay, so once again, I'll just put this back up here. This is just the minimum host mass model, and we're using Vmax as a proxy for mass. We've already seen this plot. It's the fraction of dwarfs in our, that are subhalos of something of at least a Vmax of 150. And we already know that that doesn't work. But now let's try something crazy. I'm just going to crank it all the way up to something approaching cluster size. We're going to look at the fraction of dwarfs that are subhalos of something 450 kilometers per second. And although it drops appreciably, we're still over 40%. Like is still far too efficient of a model to accurately reproduce quenching. And in fact, if we're using minimum host mass, we have to crank it all the way up to 650 kilometers per second, which is unreasonable. We know there's observational evidence that things get quenched in halos smaller than that. So it seems unlikely that host mass is really a good predictor. A much more likely proxy or parameter for estimating the quenched fraction is going to be infall time. A lot of authors have done this. And so now we're going to look at the fraction of our dwarfs that are subhalos that have been orbiting for a minimum amount of time. And I'll start with something reasonable. Let's say 4 gigayears. It's nowhere close. Within 250 kiloparsecs of a luminous neighbor, almost 80% of these dwarfs have been orbiting for longer than 4 gigayears. It's partially because the stellar mass is so low. But as it turns out, once again, we have to crank the minimum infall time all the way up to over 9.5 gigayears to reproduce the inefficiency of actual observed quenching. Is this unreasonable? It seems unreasonable, but I will say that other authors have found, I think Andrew Wetzel found around 3 to 5 gig years. Gabriela De Lucia found 5 to 7 gig years, and they all had satellites that were larger than this. So it's possible that if you extrapolate their work down to lower masses, you could be getting things like 9.5 gig years. However, we didn't really think that infall time fully captured the physics that we thought was best correlated with quenching, because something that has a radial orbit is more likely going to get quenched faster than something that has a circular orbit. So the last model we considered was kind of our, what we call the strutted satellite model. And it's basically looking at the ratio of the satellite's current Vmax to its peak Vmax, which is going to tell us something about how much mass loss the satellite has undergone. And just starting with something somewhat reasonable, we're already doing pretty well. This is things that have lost 25% of their peak Vmax. And in fact, if we get down to things that have a current Vmax that's 65% of their peak Vmax, which corresponds roughly to having lost around 70% of their mass, we can match the inefficiency of actual satellite quenching. Now, these are one-parameter models, but in terms of which parameter best correlates with quenching, we believe that it's going to be this ratio, the ratio of the current Vmax to the peak Vmax, which we think is probably also a proxy for the for quenching effects such as ram pressure stripping. Thank you. Okay, so everything I've shown you so far has been for this stellar mass range. So the next stuff is kind of more future work. This is a plot, and it's going to go over a larger stellar mass range. So this is a plot from that John Phillips made. And now instead of this distance, our x-axis is stellar mass. So now we're looking at the quenched fraction as a function of stellar mass. The green points are from Marler's work that I've been talking about this whole time. These are John's points, which are also from Sloan. And they all kind of hover around the 30% that we've been talking about. You get a slight uptick here, and it'll continue to do so because of self-quenching. But something really weird seems to, as usual, as always, be going on with the local group. These local group satellites at lower mass are almost all completely quenched. So, I mean, it kind of begs the question, is there something new going on here? Is it observational bias? Is it a statistical anomaly? It's an open question, and it's something we plan on investigating with Shea Garrison Kimmel using the Elvis suite. But it's definitely something to think about. Okay. So just flash my conclusion slides up here, and the two main takeaways I'd like you to get from my talk are quenching is too inefficient to be simply caused by a satellite falling into the virial radius of a host. Yeah, it's just too inefficient. And then finally, as far as one-parameter models go, the best predictor of whether a satellite galaxy will be quenched or not is the ratio of its current Vmax to its peak Vmax. Thank you.
Questions?
So on the last point, for the classical course of the build domain, we have some idea what their orbits are for the prop motions within our errors. But as a result, we can calculate with some error bar the pericenter. So for ram pressure stripping, basically occurs when the host halo density times velocity of pericenter squared matches the gas density and so on. If you work it all out, and you say, let me assume that every dwarf is instantaneously ram pressure stripped, or pretty much ram pressure stripped in one pericenter passage, then you get a host halo density for the corona that's quite sensible. So I guess the question that flows from that is, given that we sort of have some rough idea how ram pressure stripping works, and we know that it's much, much more efficient at pericenter than apicenter, as you alluded to in the talk, why not just sort of look at the orbits of the subhalos and sort of put on a simple ram pressure model on top of that and see what happens? Did you try something?
Yeah, that's in fact exactly what we're thinking of doing with the Elvis suite, looking at the orbital histories of the.
I'm pretty confident that will work
Okay.
very well.
Could you elaborate on how does the quenching depend on the time the satellite is spent inside the host halo? And how is this expressed in terms of the radius which you find it?
The radius, the current radius?
Within the host halo.
Sure, yeah, it's,
In other words,
it's,
is quenching becoming more and more efficient the longer the satellite is in the halo, and the smaller its radius from the center of the host halo?
yeah, I think they're related, but it's not, you know, like, since most things I think are probably on their first passage, the longer you've been in, the closer you're going to be to the center. And I think that is why infall time works so well as compared to other things. However, it just doesn't account for the type of orbit. I mean, different things are going to have different orbits, are going to get closer for different amounts of times. And that's why I think that the Vmax over the Vpeak is actually doing a better job than infall time. Because they're related. Most of those things that have been shredded have also been orbiting for a long time, but it's not a one-to-one correspondence.
They're orbiting for a long time.
Most of the things that, so the same, the group of satellites that have lost like 35% of their peak Vmax, it's a lot of overlap between that group and the ones that have been orbiting for 9.5 gig years. It's not exactly the same though. But yes, it takes a while to be shredded that much. But I'm sorry, but yeah, I don't think, I mean, our models don't really account for that. It's just looking at, if you say quenching happens at this time, it's, yeah, it's just a one parameter being infall time. If you say quenching happens after X time, what would that look like observationally? And I mean, it matches, but only after 9.5 gig years.
Good question. So have you looked at the statistics the other way around? So if you get all the dwarf galaxies that are quenched, do all of them have a massive host around?
Do all of it,
You look at all the, let's say you look at all the dwarf galaxies that are quenched, and now you look around all of those. Do all of them have a massive host around?
that's a good question. I don't think so, but actually I don't, I mean, that's not something I can look at because I'm just using the n-body simulation and saying like, if it's quenched when this happens, you know, so I don't have like an actual quenching model. It's just, if this is quenched, I'm creating the model and looking what would happen. But I think this definitely, yeah, I mean, we need better observations and many more smaller mass satellites to get a sense of that.